In this video, we'll work with parallel and perpendicular lines and planes. In this example, we're asked to determine whether these two planes are parallel, perpendicular, or neither. And if neither, find the angle between them. So two planes are going to be parallel if their normal vectors are parallel. They'll be perpendicular if the normal vectors are perpendicular. So let's look at the normal vectors for the two planes. We can read those off from the coefficients of x, y, and z in these two equations. So I'll write down n1, the first normal vector, is 1, 2, 2, and n2 is 2, negative 1, 2. To check if n1 and n2 are parallel, we can check to see if n2 is some constant multiple of n1. Well, for the x-coordinates of n2 to be a constant multiple of the x-coordinate of n1, that constant would have to be 2, but then the y-coordinate is not twice n1's y-coordinate. So the two vectors are not scalar multiples of each other, so therefore they're not parallel. So the planes are not parallel. Okay, so now let's check for perpendicularity. Are n1 and n2 perpendicular to each other? Well, to check for that, I can compute the dot product, n1 dot n2, and I get an answer of 2 minus 2 plus 4, which is 4, which is not 0. So the two normal vectors cannot be perpendicular. And so the two planes are not perpendicular. Now to find the angle between the planes, that's going to be the same as the angle between the normal vectors. It's like you've taken the angle between the planes and rotated everything 90 degrees to get the angle between the normal vectors. Now to get to the angle between two vectors, we can use dot product, because we know that n1 dot n2 is going to be the magnitude of n1, the magnitude of n2, times cosine of the angle between them. Therefore, cosine of the angle between them is given by the dot product divided by the two magnitudes. Continuing with the computation, we're getting the dot product 1, 2, 2 dot 2, negative 1, 2 divided by the square root 1 squared plus 2 squared plus 2 squared times the square root of 2 squared plus negative 1 squared plus 2 squared. That ends up as 4 over the square root of 9 times the square root of 9, or 4/9. Now I can figure out theta from the inverse cosine of 4/9, which turns out to be about 63.64 degrees. In this next example, we're asked to find the equation of a plane that's perpendicular to two planes and goes through a given point. I've tried to draw a schematic of two intersecting planes. Now the plane we're looking for, let's say call it Q. If plane Q is perpendicular to plane P1, then, as in the previous problem, the normal vector for Q has to be perpendicular to the normal vector for P1. Similarly, if Q is perpendicular to P2, then the normal vector for Q must be perpendicular to the normal vector of P2. So we're looking for the normal vector of this plane Q, and since it's perpendicular to both the normal vector of P1 and the normal vector of P2, we can find it by taking the cross product, nP1 cross nP2. Recall that we can read off the normal vectors for the planes by looking at the coefficients of x, y, z in these equations. So the normal vector for P1 will be 1, negative 2, 3. That's a negative sign carrying over from here. And the normal vector for P2 will be 1, 1, 0. The 0 because there's no z in the equation. So now I can take the cross product of those two vectors, and I get I times negative 2 times 0 minus 1 times 3 minus j times 1 times 0 minus 1 times 3 plus k times 1 times 1 minus 1 times negative 2. That simplifies to I times negative 3 minus j times negative 3 plus k times 3. So my normal vector for q is going to be negative 3, 3, 3. Now I still need a point on the plane in order to write down the equation for the plane, but fortunately I've been given a point. So I can use this point and this normal vector to write down the equation of my plane q. It will be negative 3 times x minus 5 plus 3 times y plus 3 plus 3 times z minus 1 equals 0. I notice I have a lot of 3's in this equation. If I divide everything by 3, I get a slightly simpler form of this equation, minus x minus 5 plus y plus 3 plus z minus 1 equals 0. If I like, I can distribute everything and bring my constants over to the right side to get minus x plus y plus z is equal to minus 7. I do want to mention that there are other ways to solve this problem. For example, we might have started by solving the two equations together to get an equation for the line of intersection. The direction vector of that line will also be a normal vector to the plane q that's perpendicular to both of the other planes. I also want to emphasize that there isn't any unique normal vector to a plane, right? Any scalar multiple of the normal vector that we found would work just as well as a normal vector for our plane. In this example, we're asked to figure out whether the lines L1 and L2 are parallel, skew, or intersecting. Let's figure out whether they're parallel first. The lines are going to be parallel if and only if their direction vectors are parallel. The direction vector for L1 is 2, negative 1, 3. I can just read it off from the coefficients of t. The direction vector for L2 is 4, negative 2, 5. Well, D1 is going to be parallel to D2 if and only if D1 is a scalar multiple of D2. It looks like the x component of D1 is 1/2 of the x component of D2, and similarly, the y component is 1/2 of D2's y component, but that relationship doesn't hold for the z components. 3 is not half of 5. Therefore, this doesn't work. D1 is not a scalar multiple of D2, so the direction vectors and the lines are not parallel. Next, let's decide if L1 and L2 are intersecting. Normally, to find if two objects intersect, I solve the equations together. But there's a tricky little detail here. Right now, L1 and L2 are written in terms of the same parameter t. So if I solve these equations together, I'd be looking for a value of t, the same value of t that made my x coordinates, y coordinates, and z coordinates the same. That would be, since t we think of as the time parameter, you can think of particles traveling along those lines. If we found such a t, that would be a collision point where the two particles got to the same point at the same time. But we just need the paths to intersect. One could get there years ahead of the other particle. So the parameters don't need to be equal. Only the x, y, and z pieces need to be equal. And to give it the flexibility for that to happen, the first thing I'm going to do is change my second parameter. Instead of t, I'm just going to call it s. That way, now if I solve together, I might be finding a different value of s from the value of t that would still give me the same x, y, and z coordinates. That would be like the second particle arriving at that point at a different time than the first particle, but they'd still have the same x, y's, and z's. So once I've made that key change, now I'm going to solve my equations together. So I'm going to set 3 plus 2t to equal 1 plus 4s, 4 minus t to equal 3 minus 2s, and 1 plus 3t to equal 4 plus 5s. Let me start with these first two equations and see if I can eliminate a variable, say t. So I'm going to write down my first equation and my second equation. So if I multiply my second equation, the whole thing by 2, then then the coefficients of t will be equal, and I can add or equal and opposite, I guess, and I can add the two equations together to cancel out my t's. So this becomes 8 minus 2t equals 6 minus 4s. Now I can add those together. I get 11. T's disappear as I wanted them to. On this side I get 7. Hey, the s's are disappearing too. So my equation just becomes 11 equals 7. Well, that's definitely a contradiction. And that shows that there is no solution. There's no value of s and value of t that work to get me the same even x and y coordinates. So therefore, there's no solution and there's no point of intersection. So my lines are not parallel, they are not intersecting, therefore L1 and L2 by definition are skew. Skew lines are lines that don't intersect and they're not parallel. That's possible in 3D. It wouldn't be possible in the plane. In the plane, two lines have to either be parallel or intersect. But in 3D, we could start with two intersecting lines and just shift one off the other and get two skew lines. And here's an example. This video was full of examples of planes and lines that were parallel, perpendicular, or neither. A couple of key ideas that you might want to take away from this video is, first of all, you can use the normal vectors for planes to find the angle between the planes, and in particular to check if those two planes are parallel or perpendicular. Another key and important detail is when checking for the intersection of two lines, if these lines are given in parametric form, use different parameters. For example, t for one line and s for the other, to check for an intersection point and not just a collision point, which is what you'd be solving for if you're using the same parameter.